In this video, we'll talk about what the Fundamental Theorem of Calculus Part 2 is. So recall that our previous methods to find the area under a curve, the first method that we've talked about was using Riemann sums. So we took a limit of Riemann sums. But as we saw, this method was very tedious. It's doable, and it works when we have low degree polynomials, but it is very tedious even then. It takes a lot of time. The second method that we've seen is to use geometry. So sometimes we can use geometry formulas because we get nice shapes to get our areas. So this works for linear or circular graphs. So when we have line segments or portions of circles like semicircles or quarter circles, it works really well. Our goal in this video is to find a simpler way to compute areas like this. All right, so this is where the Fundamental Theorem of Calculus is going to come in. Okay, so the Fundamental Theorem of Calculus Part 2, or I'll abbreviate it as FTC2, says that if f is continuous on the closed interval from a to b, then the definite integral from a to b of our function, so this represents the area under the curve over the interval from a to b, this ends up being capital F, where capital F is an antiderivative. So capital F, actually let me put it in a different color, capital F, where capital F is an antiderivative of little f. So it ends up being capital F evaluated at b, this upper limit of integration, minus capital F, our antiderivative evaluated at a, that lower limit of integration. Okay, so this right here, this is really amazing because it reduces the problem of finding an area to just computing an antiderivative, which often is a lot quicker. Okay, so in this video, I want to give a sketch of the proof of this result. So this is one of the key results in calculus. That's why it's called the Fundamental Theorem of Calculus. Okay, so I want to give a sketch of the proof. Okay, so the way I'm going to do this is to introduce an area function. So I'm going to let g of x be the definite integral from a to the variable x of f of t dt. So this is an area function. It represents the area under the graph of f. From a is the left endpoint of my interval, to x, where x is variable. So now, looking at this reminds me of FTC Part 1, so let's use that. By FTC Part 1, we know that the derivative of g of x, of this area function, ends up being the function inside, but we just replace the t with the variable up here, that x. So that's going to be f of x. So the derivative of g is f of x. This means that g is an antiderivative of lowercase f. All right, so what I'm going to do now is I'm going to let capital F be any other antiderivative of little f. Then what we have now is, so lowercase g is an antiderivative of little f, and capital F we said is any other antiderivative of little f. So g and capital F are both antiderivatives of the same function. So then that means that they must differ by a constant. So capital F of x is equal to lowercase g of x plus c. Since they're both antiderivatives of the same function, they must be off by a constant. Okay, where c is a constant. Okay, so what I'm going to do now is I'm going to evaluate capital F of B minus capital F of A and show that ends up being this definite integral. Okay, so now let's take capital F of b minus capital F of a and show that it equals our definite integral. Well, so using our definition of capital F of b is going to be g of b plus c, and then minus capital F of a is going to be g of a plus c. So here the c's are going to cancel and end up with g of b minus g of a. So using our definition of g of x, g of b will be the integral from a to b of f of t dt. And then minus g of a, if I plug a in here, will be the integral from a to a of f of t dt. Okay, one of these integrals, we just know what it is. The second integral, because it goes from a to itself, there's no area involved here. There's no area, so this equals 0. So this equals 0. Right, and that also is one of our integral properties. When you do an integral of some function from a number to itself, that equals 0. So thus, what we have now shown is that the integral from a to b of lowercase f of t dt, this equals capital F, our antiderivative, evaluated at b, minus capital F, evaluated at a. And I'm going to highlight this. That right there is the Fundamental Theorem of Calculus part 2. Okay, so one thing that I might notice about this, if I'm really particular, is, well, the variable here is a t, but if I look at my statement for FTC part 2 up here, I had written an x. But when I do this definite integral of this function f from a to b, that's just talking about the area under the graph of f over the interval from a to b. So it doesn't matter what I write as the variable here. This is the same as the integral from a to b, f of x dx. Okay, so we have given a rough sketch of the proof here. I'll just put a smiley face to indicate that we have done it. We have proven this FTC part 2. So in the next video, we'll start to use this to evaluate definite integrals a whole lot more quickly, because we'll be able to do this by taking an antiderivative, plugging in the upper limit and that lower limit, and just subtracting. So in terms of our goals, we finished goal 3, giving a rough proof of the Fundamental Theorem of Calculus part 2.